This is a talk that has three distinct components to it. There's what old wine in new plastic bottles. Okay, play on words there. I'm going to talk a little bit about deep learning as massively parallel processing, and I want to talk a little bit about the quantum inflection that's going to be hitting us as we're looking at doing large-scale computing in the future. These all tie into currents of what's going on inside Google. I'm involved in various things in various ways. Just to self-identify here, I'm a computer architect. I'm not a geophysicist. I'm not an algorithms guy. I'm a systems guy. And so I will approach the subject matter along those lines. I hope that works for all of you. So some of you may have seen these slides before. I love starting with this, but if I go back to 1999, when Google started, the top of the line Cray was a T90, and in some ways the last of the totally awesome custom-built supercomputers, right? You know, Gonzo vector machine, gorgeous industrial design, and the device on the right is, as I understand it, an actual picture of the first Google search rack. Okay, there are those who say that those boards were shimmed into place using Lego parts. Other people have corrected this and said, no, Duplo, you know, the big ones. But seriously, I mean, there's just no confusing what's going on. Yes, they were both doing forms of parallel programming. You're not likely to confuse the two. If I fast forward not quite 20 years, it's not quite the same thing. Now, what is great about this audience is I suspect that probably more than half of you could correctly ID which machine is which. Hint, the one with the blue lights is the Google data center. The other one is Sequoia, and yes, okay, Sequoia is getting a little bit old, but I'd love if any of you could share with me a picture of one of the newer machines with the skins off. That would be great, because yes, for the publicity shots, they put the skins on and they're gorgeous, but you know, just for maintenance and practicality, typically these things run open. Google doesn't even bother designing skins for these machines because nobody's supposed to see them. But the convergence, as it says, is not just visual. We're using essentially the same CPUs. Okay, slightly different SKUs. We're using the same GPUs, I mean literally the same GPUs, as you will find in purpose-built supercomputers. Where we do have a bit of a difference, of course, is in how you put together the network, because that is determined by the expected mission. If I'm given a bunch of processing nodes and some switches to tie them together, and I'm told I'm building something for parallel processing, then I'm likely to build something that looks a little bit what's over on the left. Okay, that's a fully connected cube. That could be the first step of a hypercube. It could be the first step of building a torus. At that point, it's ambiguous. But the point being, I'm trying to maximize connectivity. I'm trying to maximize cross-sectional bandwidth. I'm trying to have as many parallel operations flying back and forth as I can. If what I'm building is a Google data center, I'm thinking a little bit differently. Because, especially initially, we're starting to get a little bit more variation in the data centers, but for the longest time, it was pretty much a cookie-cutter approach that would evolve with the technology, but it was a 24/7 interactive search and ads kind of a business. And to do that, the important thing is you want things up and running all the time. You want no single points of failure. So the networks tended to be a Clo fabric. This is a simplified Clo fabric. We run into more stages and more inputs than that. But the notion is that any one switch goes down, any one entity goes down, you lose more, one server takes down no other servers, one switching element takes down nothing. You're just running in a degraded mode. And so you've got no single point of failure. Now that is going to make some kind of difference in your performance if you're actually trying to use the cluster as a supercomputer, which you can do. And so part of this is getting around the topology. But if you actually look at where the time goes, if you run experiments, as we did, looking at MPI latencies on our clusters going back a few years, the issue isn't really InfiniBand versus Ethernet. It may have been years ago when we were tying clusters together with 1 gig E. But at this point, the bit rates, frankly, for Ethernet frame packets have gotten beyond most InfiniBand deployments. It's not about the packet protocol. It's not about the bits on the wire. It's about the access method. It's how the application gets to the messages and gets the messages out. And in a virtualized, shared environment, like a cloud environment, public cloud environment, there is some protection that has to be there, and that protection typically isn't free. You have to be clever about it. So we've been optimizing the scheduling, we've been optimizing the binding of processors, memories to resources, and above all, we've been optimizing how the stack works to actually get things out. So we are not today proposing an RDMA interface. We do the stuff, there's lots of stuff we do in the lab that isn't available in cloud yet. But what we are doing is finding ways to bypass each of these interfaces and reduce the amount of latency. So we brought it down by a factor of 4 and the variance down by even more than that in the last couple of years. So it actually is a reasonable thing to run MPI and other sorts of HPC applications on cloud. The scaling isn't as awesome as you would get on a DOE machine, but typically the people who are coming in aren't running DOE scale jobs. And what they do get coming into the cloud environment is this simplification. This is the old wine in the plastic bottle. This is where the plasticity comes in. And that plasticity has remarkable value, because instead of trying to do the basic classic NP hard problem of doing optimal scheduling of devices on a finite set of resources, the resources are not strictly limited. Now, I won't use the infinite word. I mean, one of my jokes is that, you know, the I in cloud stands for infinite, because there's been so much marketing stuff talking about the infinite scalability of cloud. An audience like this knows better, okay? You know, no cloud person in their right mind would say that. But the point being, it doesn't have to be infinite to be useful. That flexibility is really, really powerful, because instead of having low priority jobs relegated to the back of a queue where maybe they'll run today, maybe they'll run tomorrow, depending on how you've got things budgeted, you can say, okay, I'm going to spin up some cheap instances to run these low priority jobs in parallel on completely different hardware from the higher priority instances that I'm running on the higher priced spread. So I've got this flexibility. And this has been used commercially and in research in various ways already. So this is a relatively old slide borrowed from Fermilab. I don't know if any of the Fermilab guys are present today. I know a couple of the labs are represented. But this was the work that in fact, Kenton alerted to in his talk briefly, where they're processing data from the Large Hadron Collider, and we tried this experiment of trying to teach their provisioning system, which is HT Condor, to be able to deal with elastic resources. It's used to dealing with multiple pools of resources. It is not used to having a pool that is bottomless or unknowable how deep the bottom is. But they managed to do this. And so here's a graphic. We ran this during supercomputing in 2016, 17, pardon me. No, 16, yes, of course it was. And so that's following the diurnal cycle. So there were 4 days of the conference, and at the start of the day, each day, they ramped up the provisioning coming out of the Google pool. That essentially doubled the core count that was operating during that day, and at the end of the day, we would shut it down. Now, one aspect that comes out of this that isn't necessarily obvious when we're talking about moving to the cloud is the model that Google has for maintaining its fleet. Remember I said it was sort of a 24/7 ancestry that we had, trying to keep services running and flying all the time. I thought this was a bit odd when I got to Google, because I'd never seen anything like it before. But there is this notion, there's this elite cast of crazed hackers at Google called SREs. And they are service reliability engineers. And these guys are script ninjas who are constantly refining things and building monitoring system and alarm systems, and they're watching our clusters, or more accurately, having the clusters watch themselves 24/7. And when we did this run with Fermilab at supercomputing, we gave them a heads up. We said, this is going to be an unusually big burst of jobs happening in US Central, just so you know. And they didn't really register that terribly well, because the first day when that thing ramped up, beepers were going off all over the place saying, what is going on? Have we had some catastrophic failure? You know, has the software gone wild? I said, no, we told you, it's Fermilab. You know, this is science. And again, they were able to maintain it because that's what their job is. They can see that the indicators are starting to head towards the red on network capacity, and they can start rerouting things. That's their job. That's how we roll. Now, a somewhat more complex architecture doing something the same thing. Again, Schlumberger, partner of ours, they've been working with us for a long time. And so this is actually a large enough screen where this may actually be useful and readable, which is fabulous. The point being is that their architecture is based on 3 layers. There's a top layer, which is essentially cloud resident, but it's persistent. So this is management stuff that's there the whole time. This is what the administrators are using to monitor the resources, queue up the jobs. There is a middle layer, which is dynamic. It's spun up on demand depending on what is needed. And they use a whole variety of our services. They use GPUs, they use CPUs, they're using ML, they use a lot of stuff, but it's on demand. It's according to the load. So that's using this sort of pay-as-you-go model. And that lower level is storage services, which they're using Google Cloud Storage of various degrees of hotness, because we've got trade-offs you can make between how quickly you may want to access it and how much you want to pay to have that volume stored. And so they built this layered system. It's entirely cloud native, and have ported their primary stack to it with pretty good results. One anecdote that came out of it from one of their architects relating to the use of cloud GPUs. We've recently lowered the pricing on some of the cloud GPUs, but at that time he was saying, if you just looked at the pricing, it wouldn't look like a win to use cloud GPUs versus their building full somewhere here in Texas. But the difference was that when their researchers, or the research geologists, were going through various regions, they would have to run RTM at different frequencies. And the higher the frequency, the larger the data, the more GPU memory you need, the more GPUs you need to process that particular slice of that particular shot. And in the past, that would be a work order. That would be a work order, go out for coffee, or hopefully they'd be ready the next morning with the reconfigured GPU systems. Using Google's cloud GPUs, it is just running a script. You run a script to tear down the one machine, you run another script to build up the other machine. And it's the productivity, in the end of the line, it's making the scientists more productive. That it is actually what's important to them, and we try to enable that. So looking forward, what's going on? Google is not actually the first name that comes to mind when people talk HPC, a pity, because there really is an awful lot of convergence between what we're doing, which is what I'm talking about. And so as of today, we've got enablement going on. Slurm, many of you use Slurm. Altair PBM was mentioned earlier as something that's getting to be a cloud-friendly batch manager. HT Condor, which is what Fermilab used, has hooks in it to use the APIs that we provide for management as with Google Cloud as a first-class citizen. People are using Kubernetes, various schemes around containers. So Kubernetes is something, of course, Google supports very heavily, having contributed a lot of the technology. And we have this managed Kubernetes service, GKE, that some people are using. And then because Docker and Kubernetes weren't really conceived of for running a lot of HPC jobs, we're quite interested in the stuff that's going on in terms of the Singularity work coming out of Livermore and Shifter coming out of NERSC. This is getting some traction with people, and this is stuff that can be used to help, A, get the loads into cloud, and be able to move things between clouds. And a thought that occurred to me yesterday in the talks on Exascale, I was really glad that I came early enough to catch this, is that in many ways I've been observing that cloud can be sort of a canary in the coal mine, if you will, for some of the exascale problems. Which is to say that when you're operating at a much smaller scale, but when you're operating in a Google virtualized environment, then your message latencies are going to be a little bit unstable and a little bit unpredictable. Yes, we're making it more easier and easier to manage, but then there's this cost threshold. Okay, how much are you willing to pay for that consistency? But ultimately, as you're looking at very, very large scale machines, more explicit management and coding models that emphasize a tolerance to latency jitter become important. The fact that we are running this sort of 24/7 SRE-based kind of a service, I think prefigures what we're ultimately going to have to see in these exascale systems. It's not going to be practical to shut them down completely for maintenance. They're going to have to be something that is modularized, containerized, and in some very high-level sense, hot pluggable. That's the world that we live in and have been living in for 10 years, and so one can anticipate that. And likewise, the notion that we heard several times yesterday that ultimately these machines are going to be architectural heterogeneous in various ways. We're already doing this, and the way we're seeing it is not so much at a level of I'm writing a single program that has a set of instructions in it for a CPU and instructions in it for a GPU and instructions in it for goodness knows what other accelerator. No, these are just distinct programs and ultimately distinct services that are being managed at a high level. Which brings me to machine learning and how we run it at Google. Now, most of you know this is all inspired by neurobiology. People since the 19th century have had decent microscopes and have been dissecting brains and noticing they seem to be made together of these sort of stringy things that have a large number of wires coming in and one fat wire going out. And a bit more research showed that, gee, some of these things are excitatory, some of these things are inhibitory, there seem to be weights that are positive and negative, this seems to sum up, and there's some kind of threshold function that causes a thing to trigger, but is a single signal that goes out and fans out. Really, really simple and very highly parallel. So artificial neural nets were a logical thing to try to build, and people have been building them since the 1980s. Actually, it was like late 80s, early 90s when sort of the feed-forward networks and training started really happening, and this became a potential reality. And then it was just a question of how long would it take us to have the computing power necessary to emulate all of these little neurons at the same time, and basically until about now. So what this boils down to, really good news for those of you who are used to building large parallel systems. There's very little data dependence back and forth. This is a very smooth flow of data. You're not synchronizing much of anywhere, but you have a lot of multiply adds to do, a huge, huge number of multiply adds to do. And to train the network takes several times more than to do the inference. So the team at Google built a language, a toolkit, so that they could do prototyping around things. And this is the second system. There was an earlier thing that was called dist belief that was the basis of an awful lot of the earlier Google Brain research papers. And they thought it was good, but they realized it could be better. And they did one very intelligent thing, because many times in Google, if you look at MapReduce, if you look at various other Google inventions that have been developed, published, kept proprietary, and then the outside world took the published paper, re-implemented, and then we have this sort of two versions running around, and people say, oh, but is the Google version better? They didn't want that to happen with TensorFlow. TensorFlow was open sourced from the beginning, and so what the team is using in-house and developing in-house is ultimately pushed up to GitHub and for the use of the entire community. We're not interested in making money off of TensorFlow per se. And for those of you who haven't looked at it, it's a data flow language. It's a data flow language that looks a lot like a lot of data flow languages that were popular for people to look at back in the 1980s or so. The difference is that instead the tokens that are going down these edges aren't discrete values. They are tensors. They are vectors of vectors. So this is like variable geometry, very large scale SIMD is the semantics of the thing. And so just as an example of what this would look like, because I think it's useful to just see what it is, again, TensorFlow is the primary framework that used. You could, I believe there's a version for Java. People have done other things, but Python is the preferred binding, and so one imports the thing. And a key aspect of this, which is both mostly a virtue, but it has its disadvantages as well, is that everything that's happening in this little trivial program here, where I'm setting up a constant and then setting up a couple of matrix multiplies that are being summed, nothing is actually being computed until I hit that eval method, because everything else is just setting up what the data flow is going to be. And that's actually really quite powerful if you're going to potentially have complex hardware behind it in the runtime. And because it is a very large-scale SIMD system, because it's all set up before you actually do the eval that runs everything, that makes it easier for us to do things at runtime that had typically been rather difficult and don't usually happen, which is to say we can have matmul implemented on Xeons, we can have it implemented on V100s, we can have it implemented on our own hardware or on FPGAs. You take your pick. So looking at what was happening most of the time, it's matrix multiplications. And so when Google looked at how to do this better and how to do it cheaper, I mean, yes, GPUs are expensive, but they're fabulous. But we're not using most of the silicon on a GPU when we're operating these things. And so strip it down. What do we really need to do? Well, we're doing a lot of matrix multiplications. So what's happening? Okay, so it's a aggregation of dot products. So I'm looking at A, B, and C. I can put those visualize those as faces of a cuboid. And if I look at it this way, then what's happening is I'm broadcasting each element of A down these rows of B. I'm broadcasting each element of B across these lines of A, and then ultimately I'm doing a summation down into C as in a k-way sort of reduction, where k is that vertical dimension. And to map that to hardware, we took a technique that was actually proposed, I think it was in the 1980s. H.T. Kung at CMU, if I'm recalling correctly, proposed systolic array computation as a methodology. People built a few ASICs in schools. It never really caught on at that time. Don't know why. I think perhaps that nobody actually had the killer calculation that was appropriate then. Right now, basically, matrix multiplies of relatively small values end up being worth a lot for a lot of reasons, for a lot of people. And so this notion, if you just keep that A, B, and C, the notion here is that we're streaming the values of A along, that's sort of the broadcast coming in from the left-hand side. We have preloaded the device with the contents of B, so it's basically being reused there. And then the accumulation is happening on this vertical axis into C. And the key is that I don't actually have to register all of these intermediary results. I can have a data path that's basically operating pretty much in a free-flowing manner. It's clocked, but I don't actually have to have registers there, and that makes it smaller. And so there's greater reuse without things being copied, so there's less time, less energy, and fewer data paths. So it can be a really small chip. So the first instance that we did of this was the version 1 TPU. It's kind of old now, 2015, but it has 64K 8-bit multipliers in that square. And so even though it's only running at 0.7 gigahertz, The op rate is 92 teraops, but it's 92 teraops of a very specific thing. But it's a very specific thing that's quite useful. And so that's relative, that was basically 25x what the GPUs at the time could do. GPUs have improved in the last couple of years. And 100 times what we were able to get out of the CPUs at the time. And again, with AVX 512, we can get a little bit more out of CPUs these days. But that's okay because, well, we, of course, keep innovating. And so now we have the second generation. I think Kenton had a larger photo of this up there. But this is the way we mount these things. We're on a quad board. So each chip is 45 teraflops. Now note that that's flops. This is now a floating point capable device. It's a small floating point format. You know, it does not qualify to run a legitimate LinPack. But that having been said, we're no longer talking about 8-bit operations here. So the fact that it's about half the peak of the 8-bit operations should take nothing away from it because these are larger precision operations and more complex operations. So each board is capable of doing 180 teraflops, and so 11 petaflop pods. Kenton had a picture there, so there's a large rack, which is what I thought of yesterday because somebody said, oh, well, gee, to do that, we would need a 4 petaflop rack. And I thought, we've got an 11 petaflop rack. Okay, again, not fair, not LinPack petaflops, but this is not that far out, okay? We're pushing up against what can be done there. And the way customers can access this thing is either using very high-level APIs, or we actually do make it possible for people to come in and do their own algorithms on the thing, although you can program in any language you want so long as it's TensorFlow. At some point, somebody's going to have to write a Fortran compiler for this baby, but I'm glad it's not going to be me. And the key to what this enables, and a key to what I think we've been talking about here, Kenton alluded to this also, is machine learning is a form of, I assert that it is a form of HPC. It's a form of massively parallel computation. It's very specialized, but it's very powerful. It solves problems that are really hard to solve in any other way. And one of the biggest issues isn't that the technology doesn't work, it's that people have mistaken impressions about how to use it and what it's good for. Every machine learning problem is a big data problem, but not every big data problem is a machine learning problem. You need to be able to have properly labeled data sets to train these things. And data scientists, as my predecessor pointed out, are damn difficult to find. I recall I was at a biosciences shop in the UK at one point talking to their CTO, and he was talking about the difficulty of finding good data scientists. And one of his comments was, as far as he was concerned, this is a multi-billion-dollar company, he says, as far as I'm concerned, there are 3 competent data scientists in this company, and one of them is in HR. And that's a good place to have a good data scientist, don't get me wrong. Maybe that's the first one you hire, you put there to find the others. Not crazy at all to bootstrap. But my point here is that we want to enable the use of ML by a wide spectrum of people. Not just people who are data scientists, not just people who are artificial AI researchers. We want to make this easy. So we've got a set of APIs that are canned, pre-trained. If you want to do voice recognition, if you want to do speech recognition, if you want to do translation from one language to another, we have these training sets canned, they're ready to be loaded, they're probably already running on TPUs in our data center here and there. And if you want to use it, you're a paying Google customer, you sign up, oh, I want to use this API, here's the data set I want to run into it, you get a bill at the end of the month depending on how much you've consumed. And if it's not much, it won't be much. If you're a bit more sophisticated, or you have a need to recognize something that goes beyond what those canned things would do, and I think most of the people in this room are not actually interested in recognizing cats versus dogs, then you're probably going to want to do something on your own. So we have Cloud ML. Now the beauty of Cloud ML is several-fold. One is that you've got a set of sort of canned patterns, okay? If you know it's going to be a recognition of something that could be anywhere in some space, and it's not necessarily visual space, but some conceptual space, then convolutional networks are usually the tool of choice. And we've got a selection of convolutional networks that you can just bring up and train. So you say, here's the size of the network, or here's the stack of networks I want to produce. Here is my training set, here's my test set. Go train it as a service. And it doesn't matter whether it's CPUs or GPUs or TPUs, it does what is necessary. The decision will be made on the basis of the size, complexity of the problem, available resources, et cetera. It is not the problem of the programmer to understand this. It is computation as a service. It's the first instance that we've done of computation as a service that's useful. It's something that I think we're going to continue and develop into other areas, because it's just so liberating to get the people who are responsible for problems and algorithms separated a bit from the infrastructure responsible. And it's not covered here, but Ken covered an even cooler version of this, which is the AutoML thing, where you don't even have to tell it what the specifics of the arrays of the networks are going to be. You just tell it the problem, and it will use its own heuristics and algorithms to determine what you need. If you're more sophisticated still, Cloud TPU, you can program it directly. And of course, TensorFlow is freely available. You can download it. You can run it on your home PC. All very good. But now, for the last part of my talk, and I talked a little quickly there because I wanted to have some time to do this, Google has been working on quantum computing for a while, and it's really hard to explain to people sometimes. And my belief is that it's because our brains are not wired for it. There's an evolutionary advantage in having a brain that understands Newtonian mechanics, which is to say, I throw a rock, it's going to follow a parabola. Now, it took us 10, 20,000 years to be able to define a parabola mathematically. But the intuition that it's going to start dropping and then accelerate dropping because that's what gravity does, that's pretty instinctive because that's a survival thing. Quantum mechanics, there's no reason why our brains need to wrap themselves around quantum mechanics in the same way as physical mechanics. It contradicts intuition. One of the classic examples, and one that I found quite helpful in understanding this stuff, is the classic demo that can be done if you have you can do it with a laser, but the classic model is you have a controlled source of individual photons. You fire photons into a beam splitter, you have a couple of mirrors, you have another beam splitter, and you have a couple of detectors. Now, my Newtonian caveman brain is telling me that what should be happening there is a statistically equal number of photons should be hitting on either detector. But that's not what happens, because photons ain't Newtonian critters. They're quantum things. And if you will accept, just on faith, because I couldn't derive this personally, that a beam splitter can be modeled as that matrix, and that the path on which the photon is traveling can be thought of as a vector of a couple probabilities, then I multiply that probability vector by the beam splitter. That gives me a couple of other resulting matrices. And then I run those matrices into the second beam splitter, and the result that I get is that the probability of it going to the upper target is 0, and the probability that it's going to go to the target on the right becomes 1. That seems strange, and the math only works if it is mathematically at least possible that the photon is on both paths at the same time. And again, this hurts our brains, but this seems to be the way the universe works at a microscopic level. And so taking this into computing, if I think of my element of data as a quantum bit or a qubit, it's not something that I can represent as an on-off thing. In fact, the usual graphical representation is a point on a sphere. So I can represent that point on a sphere either as x, y, z coordinates, or I can represent it as a pair of angles relative to the bases. Typically, it's done with angles. Hurts my eyes to read it, but that's the way it's done. And what is cute about this is that whereas a normal bit is 0 or 1, or let's not go into probabilistic computing just yet, even though quantum computing shares a lot with that, the quantum bit actually, just as that photon was on both paths at the same time, this qubit is, in a certain sense, both 0 and 1 at the same time. It's got a couple values that are superposed on it. And that's kind of cool. But what is cooler is the fact that if I've got 2 qubits, then the vector spaces just sort of blossom. If I have 2 bits, I can express a value, and I have 4 options that I can express. If I have 2 qubits, I can express 4 values at the same time. And that's the power. It's just exponentially more expressive if you can actually master it. So if I have 50 qubits, that state space is actually up there with a fairly large DOE machine. I don't know if it's up there with an exascale machine, but it's getting way up there. If I have 300 qubits, in principle, I can represent and manipulate more states than there are atoms in the universe. And very conveniently, if I have 333 qubits, I can represent a Google's worth. I am not saying that that is our design goal, but I'll be very surprised if we don't do at least a few runs of a 333 qubit machine just because we're Google. So to actually implement this stuff, to really do this stuff, I mean, it's all very nice to say, hey, I can do cool things with a quantum particle, but how am I going to do that? Electrons are quantum particles, photons are quantum particles. They tend to fly around and are difficult to tie down long enough to do anything useful with. A hydrogen atom has quantum states. This is well documented, it's observable, But again, they're pretty tricky because, among other things, just even wavelengths of light are bigger. So how are you going to manage a hydrogen atom? Okay, so what people came up with going back, 90s, was the notion of ions. Ions are charged atoms, but an ion is actually a quantum particle, but it's a quantum particle that you can manipulate using electromagnetic fields and light. And so there's a whole school of development on this. There's commercial companies, there's a lot of research going on in this area. When I was first introduced to the topic, it was considered to be the most promising way to build a quantum machine. And then a little bit later, somebody figured out that a superconducting magnetic field can be a qubit. It's a quantum bit, it's a quantum particle, even though it has no particle presence. And that's really convenient because this is something that's large enough that you can really, we're up to a millimeter scale here. I've got a few photos here of quantum chips. They don't necessarily have a coin or anything next to them for scale, but as long as I got my glasses on, I can see the qubits on the chip. They're visible to the naked eye. And so you've got enough room for doing some fairly complex control logic around it. The team at Google has worked with several kinds of devices for implementing these things. Fluxmons, transmons, Xmon is a flavor of transmon, Gmon, I know nothing, in fact I'm really unfamiliar with Gmon, I've read very little of the literature there. Again, I am not a quantum mechanic, I'm a computer architect, okay? But these are good for different kinds of problems. And the kind of problem the team in Santa Barbara is working on, they want to build a gate computer, a general computer, a Turing complete, if you will, generally programmable quantum computer. That's very ambitious, and I'm going to talk a little bit about how they're going about it and where we are today. So quantum logic is a little different than classic Boolean logic. You can implement Boolean logic with it, but you don't have the same kinds of gates. Those of you, I think everybody in this room understands that, yeah, you build your logic up out of ands and ors and nots, and you can build latches and all kinds of higher level constructs out of that, and that in principle, all you need is a NAND gate, enough NAND gates, and you can build anything logically. In the case of quantum circuits, it's a little bit different. Quantum circuits have to have this interesting property, and mind you, circuit is a logical sense here, it's an abstraction. But one of the cute properties is that they kind of have to be able to go both backwards and forwards in time, and so you have to have just as many outputs as you have inputs. And so you end up having these odd gates, like, the closest thing you've got to a controlling gate is what's called a C-NOT gate, or a controlled NOT, which basically inverts one input or not based on what the other input is doing. But it has two outputs. One output is typically the unmodified control input, and the other is the modulated bit. Okay? The math for that is allowable. You can build these things. Many of the other operations, as you saw that visualization, if you can keep that visualization of a qubit as a sphere, then there's lots of interesting and useful stuff that you can do by doing just operations on a single qubit, where you're basically doing rotations on one axis or another of that sphere. And so you may be doing a phase rotation, you may be transforming amplitude, you can be changing any one of the three axes there. And so if you visualize, hey, I finally get to use the laser pointer. So these qubits are the same qubits. This is a time diagram. So what is physically happening is I have a vector in these qubits. Each one of these has some kind of state. This is an operation that I am applying using microwaves coming into the device to do some collective thing, to entangle them, or to use it as a control function. And then I have steps where I'm doing unitary operations. And after some sequence of steps, again, the qubits haven't moved, I'm just manipulating them in place, then we'll do measurements of the states of those qubits at the end of the line. And that is that's the lowest level of functioning schematically depicted. Now, unlike normal computers, if I run an AND gate, if I put 2 bits into an AND gate, those bits are going to come back, the AND of those bits is going to come back out 1,000,000 times out of 1,000,000. The chip ultimately will fail probably, but intrinsically for its useful life, it's just going to do the right thing. Qubits are quantum and perverse. And the nature of these things is that the fact that I can measure it means that it is in contact enough with the rest of the universe where at some point it's going to be randomly perturbed and it's going to fall out. So the qubits are fundamentally, and we just have to accept this, unreliable at some point in time. The question is, how reliable can we make them? How reliable do we need to make them? And so where we've managed to get to, the Google team has achieved really good, the term they tend to use is fidelity. But we've achieved the best fidelity results that we think anybody has published. We've been able to get to 99.5% fidelity which is to say 1 chance in 200 that performing an operation of some kind, whether a unitary or a binary operation on 2 qubits, is going to result in one of the qubits just going south and not being recoverable. To be able to build a true quantum computer, we need to be somewhere in that 3 nines range, we believe, of reliability, which is achievable. And we need to have a decent number of qubits, probably on the order of 1 million, to build the full-fledged general computer. And so here's a bit of a depiction of what I'm referring to here. Those qubits are sitting there in place. So here they've got all their arrows. They've all aligned in an initial state. And here you can see a bunch of X gates being applied. That's an X-axis rotation. And then we have these other operations that are affecting 2 qubits. And this is sort of moving forward in time. We do some 1 qubit operations, some 2 qubit operations. And then at the end, we're going to make a measurement. And the states of those qubits, the orientations, the various phases there, and the amplitudes, depending, in the end, we have to measure amplitude, is going to be at some value. And how deep we can go and how wide we can go in terms of, because it takes essentially a hop, if you will, for one bit, a bit at one corner to influence a bit on another corner. That determines the complexity of the computation I can do without having some chance of it failing. Well, that's not very satisfying. I mean, we can make that good, but when you know it's going to fail, it's really frustrating. And so Dr. Martinez, who runs the lab in Santa Barbara, he has an analogy that I find a little forced as a classical computing guy, but it's not bad. And his analogy is that when we're building pipelined processors, we're basically using clocked logic and we're using latches to basically pick up intermediate results so that we can actually keep, we're doing it not to stay sane, but just to keep the pipelines full, just so we don't have wasted logic. And for him, the notion of a quantum system that has error correction built into it is sort of that basic building block like a pipeline stage. That allows us to have a pipeline stage where I'm highly confident that what's coming out of that stage is the real thing. It's not something that has randomly degraded, 0.5% of the time. And so a logical qubit would be composed of some number of physical qubits with enough correction logic around it to make it work. And so the notion is to actually do this at a fairly useful scale, really demonstrate. We need about 1,000 qubits with about 3 nines of fidelity, which is eminently doable with the technology we can foresee. The objective here, the end game, as the team sees it, is to make a fully fault-tolerant quantum computer. This means that you've got 2 arrays of qubits. There are various ways of doing it. The way that Austin Fowler has been, largely the conceptual leader in is it's a surface code technique. And what it boils down to is you've got 2 sets of qubits that are sort of tiling the plane. And if one of the qubits that you care about, one of the data qubits gets corrupted, flips, or changes states, this will necessarily affect the states of one of these surrounding measurement qubits. And by measuring that system and seeing when bits have flipped and when they haven't versus what is expected, you can back up and do your correction. And so if that's the objective, how do we move towards that objective in a systematic way? Because as it stands right now, most of in fact, with the possible exception of the one we have just announced, most of the machines out there today, with the qubit counts they've got and the fidelity characteristics they have, could be simulated by a big enough supercomputer. So that's sort of this purple space here. And then this is like sort of your million qubit error-corrected machine. That's going to be those are going to be very interesting devices. They're not going to replace conventional computers. They're algorithms that run just plain better on a conventional machine than you're ever going to see a quantum machine do. But that fundamental parallelism of manipulation, that fundamental density of storage that you can achieve on a quantum device is going to be very powerful for a large category of operations that are currently really expensive for us to do. So the idea is, let's build a slice of that. Could we do that? And the answer is, we think we can. So the general plan here is we want to build a quantum processor that will outperform a classical supercomputer at something. Maybe not something terribly important, but something, just to show that it can be done. Second, find an actual application that we can solve that's useful to people, and do that in a way that either can't be solved or is just way too expensive to solve using conventional means. And then finally, ultimately, the big job, build the big fault-tolerant machine. And can we do this incrementally? And the phase we're in right now is trying to build that machine that will do something that you can't do with a supercomputer. And the chip may be in the lab right now. I mean, it's under test. But it begs the question of, how do you test something that is doing something that you can't otherwise do? And you know, it's a good problem. And fortunately, these guys are pretty smart and they're good mathematicians. And what they came up with was they said there's a class of random logic circuits, random quantum logic circuits that you can generate. You can pick a depth, you can pick a width, generate these things. You can perform an analysis on a conventional supercomputer, or just, hey, a bunch of cloud processors. Where would they find those? And they can compute the profile, the statistics of how this thing ought to work within and what the error margin ought to be. And then you can compare that with the measured results. So you're basically computing what the profile of the outputs is going to be, not the outputs themselves. And that's several orders of magnitude easier. So that's the plan. And so this is what we're shooting for. So the belief is that with a circuit depth of about 40 and with 50 or fewer qubits, that's in the range of what you can do with a large conventional machine. If you want to get above 50 qubits, you're going to have to have something quantum. And there was someone who I probably sees themselves as competing with the Google team, who last year came up with a paper saying, oh, all those guys at Google and some of these academics are talking about quantum supremacy, that 49 qubits is more than you can simulate. Well, we just simulated 100 or so. And they did. That was entirely fair. However, what they simulated was a very short gate depth and a very low fidelity. And so, yes, you can. And so this kind of hard to read chart here is some work that Sergio did that basically sort of shows that you've got some equivalence between more qubits and shallower depth and poorer fidelity. It's the same problem. The problem hasn't gone away. That's the challenge remains. Once we get beyond supremacy and everyone pats themselves on their back, and I hate the term because it's not superior, it's just wildly different, then we turn ourselves into what kinds of applications we can actually do usefully. Now, I don't know that geophysics is really going to be first on the list, although there are certain optimization models and problems that I think are interesting to this audience that might be there. But in all probability, it's going to be electrochemistry. Feynman first talked about using quantum particles as computers as a means of simulating quantum phenomena, because all quantum particles have these similar properties. Again, if it's an ion, if it's a magnetic field, I perform the same operations. Those same kinds of gates that I described, these X gates and other gates, that's uniform across the whole spectrum of quantum implementation. And so the notion is a quantum phenomenon that you cannot easily observe, you can perhaps simulate on one of these devices. And so one of the classic ones is figuring out how the heck nitrogenase works, because that's an enzyme that's produced in all plants. It actually succeeds in extracting nitrogen from the atmosphere at room temperature and pressure. That's really cool, because the way ammonia is made industrially is by basically taking air and compressing and heating the hell out of it, and it consumes, by some people's estimation, 2% of the world's energy consumption is going into the production of ammonia for fertilizer. Okay, so if we can find a way to synthesize enzymes that will do that with a lot less energy, we may have bought ourselves another few years before the ice caps are gone. So I regard that as a good thing. But you got to take baby steps towards this, and we already have. So this is the photo there. That's a 5-qubit chip. I believe that's what they ran the simulation on. And this is something that gives me a lot of hope, and one of these things that to me gives a lot of credibility to this whole discipline is that they simulated the bond strength of a hydrogen molecule, H2. That's about as simple as you can get. But they were able to do it on 3 qubits and get a result that was really, really close to what theory predicted, closer than most other simulations, more conventional simulations would have expected. I'm not going to, I love this diagram because it shows just how perverse the execution of a quantum computer is if you're used to looking at conventional pipelines. But I'm not going to go into a lot of detail there, except to say that these are the 3 qubits. These are the application of control signals to them. These are sort of schematic explanations of the instruction steps. These are, the X's and Y's and Z's of these various permutations are fairly standard, but it's not unusual in quantum computing to invent really strange instructions just for the sake of efficiency. You're not going to have a stable qubit for all that long, and so if you can come up with a combination of carefully timed pulses that are going to do some fairly complex unary operation in a single step, you do it. And so you get some, these are very strange looking instructions, but each of these can be thought of as an instruction. And in the end of the game, you've basically taken that bond strength is represented by the phase of the qubit under test. That needs to be converted into amplitude, because amplitude is what we can measure with a resonator that's on the chip. So in a microscale, that's how these things work. It's talking about quality and the importance of quality. These diagrams were taken from a combination of Google work and IBM work. As you know, IBM also has an excellent and well-supported quantum program. We like to think ours is better, and we like to think that our focus on quality is important because here you can look at their work a couple years after our work on the hydrogen molecule. They did their own. The red dots are basically the IBM results. And you'll note that a more recent device, it had more qubits on it, but less precise, more of a variation from the predicted line. And their simulation of a lithium molecule is very inexact. And it's not, no, they have a real device, it really does work, but you really do need to have this high level of fidelity as you're going from operation to operation to do anything that isn't completely trivial. One of the things that makes me really optimistic that this is meaningful in the near term for quantum chemistry, that we don't have to wait for the Turing complete machine, is the progress that's been made on the quantum algorithms. Because nobody was working on quantum algorithms 20 years ago. It was a debate as to whether it was a thing. But there's some number of guys who do this, and the algorithms look strange because basically the instructions are all matrices, right? And so an algorithm is just this bizarre composition of matrices, typically expressed in Dirac notation. It is painful to look at, okay? But it's real stuff. And the guys who are getting good at this, they've been bringing down sort of the exponential number of cycles or qubits required to do these simulations really remarkably well. And so the last several there where we even managed to get an order n result, those last 3 publications are Ryan Babbage. He happens to work for us now because we said, this guy's good, we need him. And so we're pushing it there. So now for the picks that nobody saw before last week. Okay, this is, I guess, what you're all probably sticking around for. So our 9-qubit chip, which is what the last of our really seriously published results, this is one that was fabbed at UC Santa Barbara early last year. 9-qubit device, and you can sort of see it's a linear array of qubits. And very importantly, just to understand what's going on, so the control stuff is being injected in along this side. And these odd little coils, I mean, those are resonators. Basically, they are going to pick up a little bit of a charge depending on the orientation and the strength of the spin of the qubits there, that little cross-shaped thing. So that's all very nice, but how long can I build a chip linearly? It doesn't go very far, so you can't scale it quite that way. You've got to go to at least 2D. And so the idea was, and again, this is not something we've talked about until fairly recently, you take this and you slice it up. And what you do is you put your qubits on one hunk of silicon, and then you put all the rest of the logic on another piece of silicon, and you put it together the way you do an NPM for a GPU or for any one of a number of other sort of advanced bits of computing gear. So, and then you have the fact that you're running this thing in a vacuum anyway, and a vacuum, a very, very, very thin atmosphere of very, very, very cold helium, that actually ends up being a pretty good dielectric. So the next device that we did to test this, and I did not know until they published this last week that they actually put Google on the chip, right in the middle like that, and if I had been the project manager, I would have said, couldn't you put it off to one side? But nevertheless, they were highly confident that it wasn't going to hurt anything because it's sitting there right in the middle of the qubits. This is these 2 rows of those little plus-shaped qubits here. And so here we have and that's about all that's on the chip. This is just the qubits and what is required to maintain them. And then here you've got your control and your resonator stuff. And the trick is to try to make this stuff, so 11 wide by 2, it's a 22 qubit device. And so just to demonstrate that we could get this kind of thing to work. So this was not intended to be a fully functional computer chip. It was a test step along, think of it as a test chip with a lot of experimental upside. And so again, this is all about figuring out how you can tile this thing correctly. But now you've got 2 chips that you need to tile. So you basically have to make sure that your control logic and your sensors happen to have the same geometry or an appropriate geometry with just the right offset with your qubits. And so one of the things that was a little controversial among the design community there is we're using a superconducting quantum interference device, a SQUID, as a coupler for each of these things. And the first reaction of some people, but SQUIDs, I mean, that's going to generate noise. You have to bias everything perfectly. Yeah, you do. But we know of no other solution that's going to fit the geometries. And we do have pretty good control of the electronics. But it takes time to tune these babies. And so the idea is that whereas that linear cell that you saw there, the basic tiling block here is a diagonal strip of 6 qubits. And so down that diagonal is where the lines that we would use for the error correction, but we can sense on either side. And so using these building blocks of 6, we can tile, and it kind of looks like a pine cone, so the code name for the thing is bristlecone, which now apparently we're talking about. So it's a 2D grid, nearest neighbor coupled qubits. In fact, it's sort of two sets of nearest neighbor coupled qubits that overlap. And the chip has a total of 72 qubits. So it's 12 of these sets of 6. And they put it in a package and even had to put a logo on the puppy, which I think was really cute because they didn't used to do that. And here's one of the engineers actually working on setting it up for test. So this device is a device that we believe should get us to, to quantum supremacy. It may be 1 or 2 turns of silicon. I mean, so far it's coming up pretty well, but bringing up these chips really is rocket science. There's an awful lot of subtle effects that you have to deal with in setting up the wiring and the control signals. But we believe we'll be able to demonstrate a few really simple algorithms, perhaps not commercially useful, and demonstrate that the error correction can be done, demonstrate the supremacy, that we can do things that can't be computed otherwise. In the relatively near term, scaling this out, we expect to be able to do useful stuff, electrochemistry, not fully functional stuff, and then maybe as we get out into probably the late 2020s, we hope to have a general purpose machine. And so here's the team. There are a bunch of guys in Santa Barbara, amazing folks. I consider a real privilege to work with them in the small way that I do, sort of the classical computer integration part of the job. But at any rate, so hey, I ran a little bit over. Thank you very much for your attention. And just trying to say that there's more to HPC than FPUs.
A little bit of the cost of running over, at least in a day, is that we'll be limited for questions, but I'll take 2 questions. So I have one immediately here, and if you have one more, I will do one more. Oh, did you press it in? Yeah.
Fascinating talk. My question is, what about software? How compilers and operating systems are going to look like under quantum computing?
Okay, I asked the guys working on it how much I could say here today, and the answer was not very much. But what I can say is, I think it's safe to say, there's a whole community of people working on this, and there's a bunch of tools out there, some of them open source, some of them proprietary. Microsoft announced some kind of thing, embedded in Visual Studio, which is all very cool. I mean, they don't have a machine to run it on yet, but it's a neat environment. What most people are doing, I know this won't shock you, if I say that imagine something vaguely like TensorFlow, where you basically have a Python on the control plane that is calling out into a set of specialized functions. I can tell you that the team really liked early on, there's a scheme called Project Q that's out of UTH Zurich that they quite liked. They considered it to be like the best set toolkit for running simulators. But the more they looked at applying it to running a real device, they started thinking this is really not the right infrastructure for it. But if you look at the Project Q stuff, you'll see the kind of stuff that our team finds to be kind of nice. So yeah, it is as peculiar looking as that execution model I described. And so it's going to be a really interesting question because we're going to have to compose hybrid systems, right? We're going to have stuff that's going to be doing some classic number crunching. We're going to have stuff that's basically doing inference, and we're going to be sending stuff out to the quantum thing. And that's all going to be one big happy computation at some level. But it ain't going to all be Fortran.
So I think I'm going to shut it off there. And you're going to stay around a little bit?
Yeah, I can stick around for a little bit if folks got questions.
Okay. So let's thank Kevin again.